Okay, so we know about protons, neutrons, electrons. We know that atoms are electronically neutral, so there's always the same number of protons and electrons. And then that kind of brings us back to the mass and those neutrons a little bit. And so this mass number is a combination of the number of protons and the number of neutrons. So when we refer to the mass of an atom, it's the number of protons and neutrons, because originally we'd said that the mass of an electron is so small that we really don't even consider it as contributing substantial mass to the atom. Not that it's not important. It's very important. I love the electrons. They just don't contribute any sizable mass. The mass comes from the protons and neutrons. And remember that when we talk about like mass number, we're using the unit AMU, not grams. So we're using atomic mass units, special units that are used to measure things that are teeny, 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 tiny. We can't measure protons and neutrons on an electronic balance. Fractions of a gram. So we use this teeny, 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 tiny unit, an AMU, atomic mass unit. Okay, so there's different ways of representing the composition of an atom. Here's one. Often we kind of call this like the nuclear symbol, which is just fine, where you'll see the symbol of the element. So here we've got neon. And then on the side, there'll be two numbers. The larger number is the mass number. Now you'll also see this on the boxes on the periodic table that I think we mentioned in a previous video, that there's two numbers in the box on the periodic table. One's always smaller and one's always larger. The larger number is the mass. The smaller number is called the atomic number. And so these are the two numbers on a periodic table as well. The larger number represents the mass. The smaller number represents the atomic number. Now here's what's great about this, that if I know the atomic number, that's the number of protons, and I know that the mass is a combination of the protons and the neutrons, then this must be true. I can use these two numbers to determine the amount of neutrons in an atom. The number of neutrons, here it is. This is important. And I don't know why people forget this all the time. It's not crazy hard. The number of neutrons is the mass minus the atomic number. Or I think of it as the atomic mass. Mass is the number of protons plus the number of neutrons. The mass is the protons plus the neutrons. And so if I basically just subtract the two numbers in the box, the difference should be the number of neutrons. Oh yeah, I kind of remember that. And so they're kind of showing us like a neon atom. Neither of these numbers directly tell me anything about the electrons. Although if I know the atom is neutral, and I know the number of positive protons, then I also know the number of negative electrons. So in this case, neon is element number 10. Its atomic number is 10. And that's a way of identifying the element, because on the periodic table, the elements are numbered like 1 through 118. It just always goes up by one proton as I go from one element to the next. There is no other element that has 10 protons. Now, sometimes you can get into a situation where masses are kind of similar, which is why we usually use this atomic number to identify the element. So there are 10 protons. Maybe I'll put that in here, 10. I know the mass number. The mass number is 22. So then the difference is the number of neutrons. Complicated mathematics. There must be 12. Now, we'll look at some neon in a bit. I'll bring you like a tube of neon, and we'll electrocute the tube of neon and we'll see that it will glow orange. But technically, the sign is only a neon sign if it is glowing orange. Now, there are other types of signs that are real similar, but if they're glowing with a different color, it's technically not filled with neon. There would be other gases that give off different colors in these types of signs. We'll look at that in a bit. I've got some tubes that I can bring and show you. It's really cool. Okay, so this is where we want to kind of focus our efforts today. And I hope you had a chance to look at this using a periodic table. Often we use periodic tables to find some of this information. Although here they're giving us everything that we need. We're going to use some mathematics. Complete the table by identifying the number or the atomic number and the mass number for each atom. Then we'll use that data to determine the number of protons, neutrons, and electrons. Okay, so before we get into this chart, I should also mention that there are two ways of showing some of this information. So the one that we're familiar with is like this sodium with the 23 and the 11. And then I say sodium, where the top number is the atomic mass and the bottom number is the atomic number. The mass is always bigger, the atomic number is always smaller. Now, there is another way of showing kind of the same information, and it's like what they're doing down here when they wrote gold dash 197. Well, here's the deal. If I have a periodic table handy, I can look up gold. It's just kind of funky because I have to know that gold's symbol is AU, kind of a goofy one. But if I look at the periodic table, I do see two numbers in the box. There is a number 79. That's the smaller number in the box. So the 79 is the atomic number. And then the larger number in the box, now I'm looking at a periodic table that says 196.967. And so for purposes of filling out a chart like this, we round to the nearest whole number. And later on, we'll kind of figure out why that number is a decimal. But we can round to the nearest whole number. It's really, really close to 197. That number is the mass. That's the atomic mass. If you tell me gold, I can look up gold on the periodic table and I can find its atomic number. So, I mean, in the sodium example, they're giving me the symbol for sodium, which is another weird one. Na, right? Who would have expected that? And then they're telling me the mass and the atomic number, almost as if it were like a little tile on the periodic table. The other option is to write out the word and then give the mass behind it. That's the larger number. And then as long as you have a periodic table handy, or here they're telling us, you can look up the atomic number. It's the smaller number in the box. It's the whole number. And so, for example, if I see this sodium symbol, the atomic number will be the smallest number. That's going to be the 11. The larger number is the mass. That's the 23. By definition, the atomic number is the number of protons. And as long as the atom is neutral, the number of protons equals the number of electrons. So the protons are positive. I'm going to put that in there. Positive protons, negative electrons, neutral neutrons. So the positives and negatives have to be the same. The neutrons can be a little bit different though, because again, if I have a couple extra neutrons, that's not going to change the balance of charge. All it does is add mass and stability to the atom. And so if I want to find the number of neutrons, I have to remember that the mass is a combination of the protons and neutrons. So if I know there's 11 protons, I just subtract. So we should have a big fat 12. So I'm going to mark that in here, the mass, which equals the protons plus the neutrons. Awesome. So we're just going to see if we can fill this out, and hopefully you had a chance to look at it, and we'll see if you got it right. So the second element down is sulfur. Sulfur is S. The smaller number is the atomic number, 16. The larger number is the atomic number, the atomic mass. Hello. By definition, the atomic number is the number of positive protons, and if it's neutral, it's also the number of negative electrons. To find the neutrons, we just subtract. The mass is 32. I'll subtract off the 16 protons. There's also 16 neutrons, which is cool, but it's also just fine that sodium had an extra neutron. Totally fine. And then really we do the same thing with the silver and the gold. The atomic number is 47, and if you look up silver on a periodic table, it's symbol Ag. They really picked some kind of goofy ones here. So yeah, if I look at a periodic table, Ag has a 47 in the box. It also has a number, if I'm looking at my periodic table on the wall, 107.868, which is really close to 108. And so the number at the end of the word, that's the mass. So the mass is 108. By definition, the atomic number is the number of positive protons, which is the number of negative electrons as long as it's neutral. And now I subtract. Whoa, this is interesting. Okay, so there's a mass of 108, and then I'm going to subtract off the 47 protons to get, yikes, 61 neutrons. That's really weird, isn't it? There's a lot more neutrons compared to the protons and electrons. It's totally fine. Don't worry about it. Similar with gold. If I look in the box, yep, gold is number 79. Its mass is darn close to 197. There would be 79 positive protons, 79 negative electrons, and if you have to pull out a calculator, you can. Now we're going to subtract. So we'll say 197 is the mass. I'm going to subtract off the protons, and what's left should be the number of neutrons. I'm getting 118. Whoa! That's a lot of neutrons, right? Okay, so here's something that we'll talk about when we do like nuclear energy and nuclear reactions. But do you notice that for the sodium and the sulfur, the number of neutrons is pretty close to the number of protons? And yeah, there's one extra neutron in sodium. And then they're both relatively small atoms. But then when you get to silver and gold, they're pretty big atoms. There's a lot of particles in the silver and gold atom. And that's where I notice that the number of neutrons is a lot more, noticeably more, than the number of positive protons. Can you think of a reason why that might be? That why in a bigger atom with, we're talking like almost 50 and 80 protons, why do you think you need more neutrons? A lot more neutrons. We're not talking a 1-to-1 ratio anymore. Not even close. Did you maybe think about the fact that protons are positive and like charges repel? And so if I have, get out of there, if I have like 79 positive protons, that's a lot of positive charge and a lot of potential repulsion. Which, I mean, if we just had all these positive charges, like why would the nucleus even hold itself together? Wouldn't it like explode or something? Well, it does turn out that the more protons you have, eventually as the atom gets really big, we need more than a 1-to-1 ratio of protons to neutrons. We need a lot more neutrons to kind of get in between all the positive protons and prevent like the nucleus from exploding on itself. We try to like keep those positive protons kind of away from each other to help prevent some of that repulsion. And that's why when we get to these really big atoms, don't freak out if you notice that, whoa, that's a lot of neutrons. Yeah, it's probably right, especially when you have a large nucleus.